Welcome friends, Igor is here, and in this video we will work with the dimension of vector spaces. In this lesson we will learn to distinguish between finite dimensional and infinite dimensional vector spaces. We will define the dimension of a finite dimensional vector space, and we will compute the dimension of several vector spaces. Let's get started. A non-zero vector space is called finite dimensional if it has a finite basis. A vector space which does not have a finite basis is called infinite dimensional. Also, the zero vector space does not have any basis whatsoever because it only contains the zero vector, and any set of vectors which contains the zero vector is automatically linearly dependent. However, by convention, we are going to regard the zero vector space as finite dimensional. Here are some examples. The vector spaces of column vectors, of polynomials of bounded degree, and matrices are all finite dimensional because in the previous video we did find finite basis for each of these spaces. In contrast, the vector spaces of infinite sequences and all possible functions, which were covered in this video, are infinite dimensional because they do not have finite basis. For example, it should make sense to you that it is impossible to get all possible functions simply by taking linear combination of a finite set of functions. Linear algebra studies only finite dimensional vector spaces, and infinite dimensional vector spaces are usually studied in, for example, functional analysis. Let's try to figure out together how to define the dimension of a finite dimensional vector space. So, we would like to say that the dimension of a vector space is the number of vectors in a basis for that vector space. But there is a problem with this definition at this stage of our understanding, because this definition depends on choosing a basis for a vector space. But what if you can choose another basis for the same vector space, and that other basis will contain a different number of vectors compared to the first basis? In fact, this will never happen because any two bases of a vector space will always contain the same number of vectors, but we need to prove this. Suppose we have a set of t vectors that spans a vector space V. Then any set of t plus 1 or more vectors in this vector space is automatically linearly dependent. Let's take an arbitrary set R of m vectors in the vector space V. We are going to assume that m is greater than t, and we will prove that this set is linearly dependent. To prove that the set R is linearly dependent, we will construct a non-trivial relation of linear dependence on this set. To do this, we must find a set of m scalars x1, x2 through xm so that not all of them are zero, and the linear combination of the vectors from R with these scalars is equal to the zero vector. Now, let's use the assumption that the set S of vectors v1, v2 through vt spans the entire vector space. In particular, each of the vectors in the set R can be represented as a linear combination of the vectors in S. Notice the pattern of indices in the scalars in these linear combinations. The first index in the scalar corresponds to the v vector. The second index in the scalar corresponds to the u vector. The reason for this choice will become clear very soon. Now we are going to substitute for each vector u its presentation as a linear combination of the v vectors into the relation of linear dependence. Next, we will use several properties of vector spaces to rewrite this linear combination in this way. Please go through this computation, identify every single property that you will be using to rewrite this expression in this way. I just quickly did this mentally, and I counted 5 out of 10 properties of vector spaces that had to be used to make this transformation. This allows us to start with a relation of linear dependence on the set R, which contained u vectors, and transform this into a relation of linear dependence on the set S, which contained the v vectors. Here comes the tricky part. We do not know that the set S, which contains v vectors, is linearly independent, but this relation of linear dependence for sure is satisfied if every scalar is the zero scalar. We're not saying that this is the only solution. All we're saying is that this is a solution to this relation. But now, do you see the convenience of our choice of indices for the a scalars? You should recognize this as a homogeneous linear system where x1, x2, xm are the unknowns. This linear system has t equations and m unknowns. Our initial assumption was that m is greater than t. So we have a homogeneous linear system with more unknowns than equations. We know that such homogeneous linear systems always have infinitely many solutions. Among infinitely many solutions to this linear system, we can find non-trivial solutions. But this non-trivial solution for the axis will give you a non-trivial relation of linear dependence on the set R. This proves that the set R must be linearly dependent. Now we are ready to prove that all bases of a finite dimensional vector space have the same number of vectors. Suppose V is a finite dimensional vector space and we have two bases for this space, B and C. A basis is a set which is both linearly independent and spans the vector space. So first, let's think of B as a spanning set for V and C as a linearly independent set. By what we just proved, C cannot contain more vectors than B. But let's switch the roles of B and C now. Let's think of C as a spanning set and B as a linearly independent set. This means B cannot contain more vectors than C. The only possibility, therefore, is for B and C to contain the same number of vectors. And now we are ready for the main definition of this video. The dimension of a finite dimensional vector space is the number of vectors in any basis of this vector space. This definition is unambiguous because we just proved that any two bases of the same vector space always contain the same number of elements. Therefore, it doesn't matter which basis you take. And now, let's compute dimensions of some common spaces. First of all, the dimension of the vector space of column vectors of size m is equal to m. This is because we have one basis for this vector space which contains exactly m vectors. The dimension of the vector space of polynomials of degree at most n is n plus 1. This is because we have a basis which consists of all possible monomials. There are n plus 1 vectors in this basis, so the dimension of the space is n plus 1. Finally, the dimension of the vector space of m by n matrices is m times n. Once again, in the previous video, we have found a basis for this vector space, and this basis contains m times n vectors. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will study properties of the dimension of vector spaces. I will see you later.